All right, so does it work? The microphone, it seems, it works, right? I don't know, but you can hear me, right? Okay. So yeah, so last time I introduced you to expander. What are like what is it? And basically, expander is a graph such that well connected, but can be sparse too. And the concept that capture the expansion is the main thing that we talk about is conductance. And if a conductance is something like if it is like a 1 over polylog or something, or 1 over log n, then we say that a good expansion, a good expander. If it is like smaller than that, or like think of 1 over root n, then bad. Like it's not very well connected. But it turns out that I will not prove this to you, but computing conductance exactly is NP hard in general graph. Actually, you can try to think if a graph is a tree, you can do it in polynomial time. But in general graph, it's NP hard. So today I will tell you how to approximate it, how to know what is approximately within log n factor, what is a conductance, which means that if you can do this, you know up to some extent how expanding is a graph, if the graph is a good expander or not. Right? And the plan is actually to go through something that looks totally different. I will tell you about metrics and metric embedding. That's the first thing. And then I will try, and we will talk about L1 metric. And then we will connect this L1 metric to something called cut metric. And these will be the two ingredients. And once you know about these two things, then we will I'll tell you about the approximation algorithm. Okay, so let's start with the first thing, metrics. So metric is just something that is just a mathematical notion that capture a notion of distance, right? So suppose that you have a set X, think of it as a set of points, and then there is a distance function d that kind of for any point x and y in the set, you can measure d of x, y, measure the distance between x and y. Yeah. And so x and d is called metric space or just metric. If d satisfy the following constraint, you need d to satisfy this to say that d and x and d is a metric. So first of all, the distance between x and itself is 0. And the second is that it's symmetric. Between 2 points, go to x from x to y and y to x. These are the same number. So both of these are kind of intuitive. The last one is also very intuitive. It's called triangle inequality, which means that if you have point x and point y, and then you have point z, then, maybe I draw it this way. You have point z and y here. So what it says that the distance from x to y must be at most the distance from x to y plus from y to z. So this is just like the property of distance in Euclidean space that we are really familiar with. But we just pick this as a property and define it as some property that D must satisfy. Okay, so this is just three things that metric need to satisfy. Any question about this? Okay, so let's just see some example of metric, right? So the first thing is, if think of everything is in the line. Suppose that I have a set X, and there is a mapping that map everything in X, like X is maybe like a X1 up to Xn, and then I can map everything into the real line. So F1 here, X2 is maybe here, and so on. So it's just in a real line. And I say that the distance between X1 and X2 is just a length between the two things here in the mapping, right? So let's just try to verify this, that D is indeed like D indeed satisfy all of these things, right? So these two are kind of trivial, right? And the last one here, it will be true too, right? Not sure if, yeah. So if you have like X and Z here, and then maybe Y is here, then so distance from X to Z, which is this, is at most from X to Y and back. And if Y is here, that's fine too, because from X to Y, and then from Y to Z, still at most the blue distance. Right. And yeah, there are other, so this is kind of something that we have very good intuition about. We can talk about L1 metric. So let's just look at this because it will be the main object in this lecture. So L1 metric is just kind of very similar to line metric, except that it's more than one dimension. So that is, you say that you have a point X, and now you may map each point into some point in the space. It can be m dimension, and then the distance between 2 points is measured by this L1 norm, which is you sum up the, like for each coordinate, you measure the difference between them for each coordinate. So which in picture it would the distance would be this, right? This plus this thing. Yeah. So is it note that this is really just a sum of line metric, right? Okay. And cut metric is just another example. So how do I define cut metric? So it's like this. Let's say that you have a set X, and then let's say I fix a set S in X. Then we just say that, okay, for any point, if they are on the same side of a cut, then the distance is 0. Otherwise, the distance if x and y are on the same side, then I just define that distance here is 0. Otherwise, if they are on the different side, distance is 1. So this you can try to verify yourself too that this is indeed a metric, okay? As an exercise. Another one which is good to know is shortest path metric. Here, so I will say that the metric is the shortest path metric if, suppose you have a graph, and the node of the graph is a set X. Okay. And then I will just define this, like if I have two nodes, X and Y, the distance between X and Y is just the distance in the graph, the length of the shortest path in the graph. And if I have that here, then the distance, this is the X, Y, and the Y, Z. And here you can verify as well that this is indeed a metric. The function D is indeed a metric because you have triangle inequality, right? Y, like a distance from X to Z, well, it will be at most like distance, this thing plus this thing, because this is one path. This is one XZ path. So the distance is of X and Z is at most this sum. Okay. All right.
In the case of cut metric, if you come away, like both are equal and they belong to S, then it's not 0, right?
So if they both belong to S, then the distance is 0. If they are not, both of them are not in S, then the distance is 0 too. Yeah. All right. Okay, so that is just a metric. Now, I want to talk about another concept called metric embedding. But before that, let's try to get some motivation. That is, different metric is different in the quality. So if you want to compute distance in some metric, sometimes it's more expensive than computing distance between 2 points in another metric. And let's just see example, right? So if you have a shortest path metric, right? Then if you are given two nodes S and T or X and Y, to compute distance, it's just shortest path problem. And that, how long does it take? Well, at least linear time. You need to kind of read the whole graph just to even check if the 2 points are connected or not. It takes linear time. Yeah. So that is when you want to compute things from scratch. Or otherwise, you might need to spend to remember all possible distance, and that takes a lot of space too. If you remember all pairs, then that takes n squared space. Either expensive time or expensive space. But suppose somehow that your data is represented as L1 metric and with small dimension too. Think of K maybe like 10. Then it's very easy then to compute distance, right? Given 2 points, just read the coordinate of these 2 points. Nothing else. You don't need to care about everything else at all. Just 2 coordinates. Compute that in constant time. So that is it seems to be great. It's very good very easy to compute distance. So that means that if you are given some metric, X and D, if somehow even if it is not originally from L1, if somehow you can represent it as a L1 metric with some distortion that I will define, if you can somehow do that, then it will be kind of good for you. It's very like nice. You can compute this time very fast. In other words, you kind of like L1 is kind of friendly, and you want to embed metric into a friendly metric. So let me tell you like what I mean by embed here, and what it means to have like a small distortion that I mentioned. So now formal definition. Think of you have two metrics, right? X d and x prime d prime. And if somehow I have a mapping that map each point in x to some point in x prime, such that after I mapped, right? After map x, the mapping of x and y, I have that the distance in d prime is approximately the same thing as the distance before I map. So the distance is kind of preserved, it's sandwiched between like this thing sandwiched the original distance with some factor alpha. So it means that after I map like thing like this, you have x here. This is x prime, right? X, y. I map it using f, and this is then if the distance, the blue distance, is approximately the same thing as the purple one, and by approximately I mean they are like this is d prime of between these 2 points. If they are kind of the same within alpha factor, so this is a picture. Then if that happened, then we say that first of all we will say that f is a metric embedding, and f map the first metric into the second one with distortion alpha. So if this is true, like if the distance is preserved for every pair of points, then we say that you map the first metric to the second one with distortion alpha. Is the definition clear? All right. Yeah. So equivalently, we can just say that x can be embedded into another into the second metric with distortion alpha, and this is just a notation. Although we will not use it, but this is a mathematical notation. And if alpha is 1, then it means that there is no distortion at all, right? The distance is perfectly like preserved. Then I said no distortion, or distance preserving, or we can also like there is a term called isometric. So for example, sometimes like when I can map, like let's say that I also will just say that a metric xd is maybe think of this as L1 first, but I will call it is, this metric is an LPK metric. If you have an embedding that embed this metric into some other metric x prime, and this x prime is a LP metric with dimension k. That is, if you have a metric that, and you can embed it into L, into some other metric, and that is the L1 metric, then you could, and if there is no distortion at all, just say that the first metric is an L1 metric too. So, for example, let's try to see one example of this definition. So, a cut metric.
While doing the embedding, we never want to increase the distance. We always want to reduce it, as per that definition.
No, you never, you can only reduce it, yeah, right. But you will see later that given a metric, after you scale, then it is still a metric. So it doesn't really matter, even if I change this to 1 over alpha here, then it will have the same kind of meaning. Yeah. Okay, so first, let's see this, right? A cut metric is a line metric. So why is that the case? Well, if you have this as a cut metric, then what you can do, you can, for example, maybe I draw it this way. Then I just map everything in S. I define a mapping such that I map everything in S to 1, everything else to 0. So everything else here map to 0, and here is 1. And then you can see that now, after mapping, this mapping is really like an embedding that gives no distortion at all. Question about this? You guys seems very quiet. I'm not sure if, is this okay? All right, good. So, so now comes the very powerful statement. I was saying that L1 is friendly, it's good, it's like a very nice. But it turns out that if you're given any metric, can be like a metric defined from a graph, anything at all, you can embed any metric into L1, which is friendly and nice. And actually it has small dimension. The dimension is like a log n square, kind of smallish. And the distortion is just log n. So that is kind of, should be surprising. Everything is actually you can map into something friendly and with small distortion. So in other words, like a given x, you can map this each point in x such that the following is true. Like the L1 norm here, the distance in L1 is kind of preserve the original distance within log n factor.
Is the dimension of points in x?
Yeah, the dimension is log square.
No, in x.
In X, there is no notion of dimension in general metric, right? In general metrics, you have X, which is just some set, and D, which is just a pair of distance. For example, the graph metric, like a shortest path metric, it's just some metric. Yeah. But you can map into like a real space with L1 space with small dimension. Yeah. And moreover, this mapping F, you can compute it like in n square time, fast. And moreover, if this metric, for example, is defined from a graph, it's like a shortest path metric, you can compute it in like a linear time, near linear time. By the way, throughout the course, I will use O tilde to hide the polylog factor. Right. So just by this statement, you can see that this can be quite useful. Because, like, suppose that you are given any graph G with n node, and it can potentially have like many edges, n square edges. Then this mapping says that, okay, you can label each node with like a log n square numbers. This is just the dimension here. And then if you want to estimate the distance, just read the label and get like you get log n approximation of the distance in log n square time. So that's like a fast distance data structure immediately. And what's more important, like what is important also is that the total space here is just like there are n nodes. Each node you have log n square number. And this is sublinear in number of edges. It doesn't matter if you have n square edges. So that is kind of nice already. We will use this in a very different way, actually. And you will see. I want to note that, by the way, that each coordinate in this mapping F, each I coordinate is not some crazy number. It's like always, we will see in the proof, and we will prove this next time. But each coordinate will be like actually like a d of xy for some y. Like some original distance between x and some other point. So this is like this is by Bourgain, yeah. But the dimension that he proved was like something like exponential in n. But this is improved to log square, so a lot of improvement. Yeah. When you will see this next time, how come this is true. Before moving on, like this is just some example of something called metric embedding. And you just see, like this is just one application of metric embedding. You want to embed something to something which is more friendly. There are more examples, and you might see more later in course. All right. So that is just the first ingredient. Any question before we go to the next one? All right. So next, I want to say that L1 metric, in some sense, is also very simple. Like, so you have seen that a cut metric is a line metric. Like you can map a cut. Like a cut metric can be represented as a line, like just very simple line. Like a lot of point is 0, a lot of point in 1. So that and line metric is just a very special case of L1 metric. It's just like so a cut metric is just an extremely simple L1 metric. But you will see the inverse now. We will see that this is like kind of the inverse is kind of true in some sense. That is, any L1 metric also is just a combination of a lot of cut metrics. I will prove this. So we have seen that like any metric is similar to L1 metric with some distortion, log n. Now, L1 metric. Now we have any metric and L1 metric, which is quite like a nice and friendly. Now there is a cut metric, which is super simple, and now like even L1 metric is like just a combination of cut metric. So things are like can be simplified a lot. So let's see what I mean. Before proving that formally, so we need some formality. So first of all, given any endpoint metric xd, you can just think of d, instead of mapping, you think of it as a vector in n choose 2 dimension, right? So it's just a vector d such that like the first coordinate is just like a distance between 1, 2. Next one is distance between 1, 3. So it's just a vector that encode all pair distance. All right. And by the way, if the metric is finite, then you can like D basically encode everything about XD. It's because given all pair distance, that's all information about the metric. So let's just think of D itself as an endpoint metric too. Observe the following. If you have two metrics, D1 and D2, if I sum them up entry-wise, this sum is a metric as well, right? Maybe can someone tell me why, why this is true? Like for example, why triangle inequality is true for this.
The inequality points in the same direction, so when you add them, it's still the same.
Yeah, great. Thanks, Harry. Also, if you have that D is a metric, also like if you scale it by any non-negative number, it's also a metric. Right? I mean, like to verify that the new thing is a metric, you just need to verify these three things. These three things, and it's kind of obvious. All right. So in other words, like if you have two metrics, any non-negative combination of them is a metric. Or if you have like n or k different metrics, like any non-negative between these k things is a metric too. Okay. Yes?
Could you explain what it means by 10 codes everything about X?
10, which one again? Sorry?
The second statement, let's refer to D.
Oh, okay. What I mean is that instead of writing that X and D is a metric, I want to say that let's call D itself as a metric, because given D, you know everything about this metric XD.
You're not explicitly mentioning the vertices of.
Yeah, let's just like don't explicitly talk about X, because yeah, all we need to know is just the distance between any 2 points in X. Yeah. And now I define a cut cone. So cut cone is just, it contains all non-negative combination of all cut metrics. In other words, in mathematical term, so it's all matrix D such that this is D equal a non-negative combination of a cut matrix. So each coordinate here is non-zero, and each of this is a cut metric. Like each of them is like endpoint cut metric. So if you know the term, this is like a convex cone of all cut metrics. But this is just the definition, and you can see that from this fact, right? Anything in this cut cone is a metric as well. So that's cut cone. Our goal is to say that any metric which is L1 metric is inside a cut cone. It's a metric, like cut cone contains all L1 metric. That's our goal. But we will try to prove something much like special case of that. So, which is this step. So we don't look at L1 yet. We look at line metric. And even simpler than that, we look at the line matrix, which is inside like 0, 1 interval. So what I mean is that I call XD is a 0, 1 line metric. If basically there is a mapping F such that it maps all points in X in between like between 0 and 1. And the distance between 2 points is just, the distance within this interval. All right. So you can see that this is just a special case of line metric, and which is in turn a special case of L1. This is not a cut metric. A cut metric is actually a special case of this one, because a cut matrix, you map all points to either 0 or to either 1, right? Here I allow mapping to map to somewhere between this interval. Yeah. So yeah, cut metric is like a 0, 1 line, but not vice versa. Yeah. So now comes the crucial step. Yes?
Is it clear what we call it, like cut cone? Because unless I'm misunderstanding, it's just like all the linear combinations of like existing metrics, right? So like what is the relationship between that and like the cut that we talk about?
The reason we call it cut cone is that it's just cone means that the word cone, the word convex cone really just means non-negative combination of things. Yeah. And it is not just linear combination because you don't allow negative.
Yeah, sorry, I misread.
Yes. All right. All right. So now this is a very important step. Okay. So just consider this metric, which is this 0, 1 line metric. Okay. Now, so it's just the thing in 0, 1. And think of this mapping if it map thing into thing inside interval. Suppose that I choose a threshold t between 0 and 1, threshold t. Let's say that I choose it uniformly at random. And I define a cut, st. It's just like everything that, all the points here basically, that all the point that is mapped before t. So this is st. Okay. Now, for every point u and v, I want to say that the expected distance of this cut, like the distance of between u and v, defined by the cut matrix ST, in expectation is just the original distance. So let me repeat the statement just to so that you absorb it. So is the definition of ST clear? You choose a random threshold. ST is just everything before that. Okay. And now if you fix ST, this is just a cut, and you can define a cut matrix based on ST, right? Now you ask, okay, what is the between any node u and v? What is the distance between u and v with respect to a cut matrix ST? Now this cut is random, and the statement just said that, okay, in expectation, the distance defined by this random cut is just original distance. Okay. So if this is true, what does it mean? It means that D is really just, think of D as a vector, like n choose 2-dimension vector, right? D is the same thing as D is simply the distribution of a cut matrix. It's just like,
D is a 0-1 line metric.
yeah, D is 0-1 line metric. But, and like a cut metric is a bit simpler than 0-1, but now you can see that in expect, like, it's just, D is just an average of a bunch of cut metric. So, and this is actually kind of easy to prove. The important thing is about the statement that a 0-1 line metric is just it's just an average of cut metrics. So let's try to prove it. Okay. So okay, let's fix u and v, right? And let's assume for without loss of generality that u is okay, I have a picture. Let's assume without loss of generality that u is before v. So what is the expected distance of between u and v with respect to a cut st? This is like, because the distance here is just 0-1. So this is exactly the probability that the distance is 1. And when is it the case that distance is 1? This is the case when like you choose a random threshold t and it separates u and v, right? And when does it happen? It just happens only when t is between these two things. Yeah, yeah. So yeah, yeah. Thanks. Yeah. Yeah, something like that. Okay. And this is exactly just the distance, like between the 2 points, which is the distance between u and v in the line metric. Okay. So the message is D is just it's just an average of cut metric. So let's rephrase this in an equivalent way. If I say that, okay, let me like, given x, I arrange x in this way, like put the first one first, the next one second, the third, like sort them basically in the line, and then define S prime I to be the first I guy in this line within this interval. And define alpha I to be the difference between so in this one alpha alpha 1 is this and alpha 2 is this thing and so on. Then we can just what we have shown before is just the same thing as saying that D is this thing, right? So why is that the case? Because let's see, right? When you choose a threshold cut, ST is always of this form. It's S prime I for some I. It's a threshold cut, and we just showed that D is the expectation of DST, which is, and DST is always of the form S prime I. So we just need to just expand this thing, write it down. It's just a sum over all this. You ask what is the probability that ST is S prime I, and this probability is exactly alpha I. So what we have proved is just the same thing as showing this thing. Okay. So I kind of just repeat things in the different way. Yeah. So what can we conclude? We can conclude that any 0, 1 line matrix D is just a non-negative combination of n minus 1 nested cut. There are not just any cut metric, it's threshold cut which are nested. Very structured. And in particular, it means that D is in a cut cone. So now, okay, that's a special case, but it's a key case. It's a crucial one. Now it's kind of easy to generalize. So let's generalize this to just any line. Any line metric is not in just one interval. So any line matrix. So now the mapping is it mapped into reals. Okay. So first of all, if you're given a matrix XD with a mapping F, so thing maybe this is it maps X to something between this interval, where this is 10 and this is 100. So X is mapped into something like this. I can assume actually that no, let me tell you this. Suppose that so it maps to this interval between 10 and 100. Suppose that I say that I want to change the mapping a bit by translating the whole thing by 10. You can see that the distance, it doesn't change at all. So without loss of generality, I can just say that I translate things so that the minimum guy is at 0. Right? So I will just assume that. So now it means that the matrix D is such that the mapping is not just between anything in real line. I assume now that the minimum guy is actually at 0. And another guy is like a maybe alpha. So now like the mapping is like I map x from 0 to something in alpha. Think of alpha maybe 100. Okay. But now this metric D is just the same thing as 0, 1 line matrix after some scaling, right? So if I have D and I look at D over 100, then this thing is a 0, 1 line metric. And what do we know about this thing? It's a 0, 1 line metric, and which already show that this thing is just the average of some cut, like nested cut metric. If D over 100 if D over 100 is a non-negative combination of cut metric, then D itself is just will be the same, right? Will be a non-negative combination too. So which means that, okay, now we have that any line metric D is a like non-negative combination of n-1 nested cut metric. So that is now we now generalize to line. Now actually, can someone tell me how would you generalize it to L1? Right, right. Like, it's a sum of line metric. So, so if it's a sum of k many line metric, then it will be a combination of nk many. Like, if a sum of this one is a sum of k line metric, then this metric D is combination of nk many cut metrics. So it's exactly that. So just to rephrase, right? What does it mean to be like a L1 with dimension k metric? So you have mapping such that F map to k dimension space. And yeah, you look at D is a sum of k line metrics because yeah. Do you need me to explain this actually? Right. Right. So now so because this is a sum of k line metric, then you have that any L1 metric of dimension k, if they have endpoint, is a combination of n times k minus 1 cut metric. Are these cut metric nested?
Yes.
So who do you think is the case? And who don't think so?
What does it mean to be nested again?
So by nested, I mean each cut is like, if you take any two cut, like one of them will be like include inside another one, or vice versa. So in the case of line metric, right? You have that the cut that you define always look like this. It's like if they intersect, one of them is like inside. Yeah.
So when you do that for more than just on the line, like multiple dimensions, does it kind of still look like that, but just like if it was in 2 dimensions, does it kind of still look like that, but it's like, I don't know how to.
Yeah, I think I got what you mean. Like it will be nested for each dimension, right? So, like you have you have nk many cut matrix. Like you can group them into like a k group. Each of them is n-1 metric. For each, like maybe it's easy to draw. Maybe into dimension. Maybe you have this point. Then the cut that you will define will be like the first cut is here, the second cut is here, third cut is, and then you will have another set of cuts, which is this. So good. All right. So and I want to define this, like given, let's say that D is a L1 metric with a mapping F. I want to define script F to be just this collection. It's just the purple thing together with the green thing. Call it this is a collection of all cuts, such that D can be written as non-negative combination of these cuts. Yeah. So we know that given any L1 is a non-negative combination of a bunch of cuts. Call those collection of cuts script S of F. Okay. And you can see that everything we discussed so far is really algorithmic. So like if you have a metric D and a mapping F, how do you compute the cut? How do you compute this collection of cuts? So you just look at each dimension, sort them, define this like nested cut. That's it. That's how you get this collection of cuts. And how do you define like the alpha, the coefficient? When you sort them, yeah, look at the distance between any two, right? That's alpha. Okay. Now we are we have all the ingredients. So let's take like 1 or 2 minute break, and then if you have any question, feel free to ask for now.
Why is it called cut cone?
So non-negative combination of two things is a cone between defined by that two. Like linear combination of two things is just kind of the same thing as cone, but you allow a negative coefficient. But now if you talk about, okay, why a cone, right? So it's like kind of kind of look like a cone.
So if you see 3 dimension, it looks like this basically, the first quadrant.
Oh yeah. Great.
Even in 2 dimension, it's the first quadrant.
Yeah, let's draw 2 dimension. So this thing. So what is the non-negative combination of this one x1? It's kind of this, right? Non-negative combination of this x2 is this thing, and you allow like everything here. This is like some alpha x1 plus alpha x2. Yeah. pyramid maybe. Okay, let's continue. So now we have everything we need, and the plan now is the following. Not like we kind of make a long digression, but the goal is to approximate conductance of some graph, right? And what I will do first is actually I will define some other concept like phi of GH, H expansion, that will kind of generalize a notion of conductance. So if you can approximate this one, you will be able to approximate this one too. It's just some generalized notion. Why do I do this? Because it will make some notation a bit simpler. And why not? We can solve a stronger problem. Next, when this is like a very basic framework of approximation algorithm, right? You want to approximate something. How to do that? Try to write it as an LP. Try to write that thing as an LP, compute that, solve that LP, and hope that the thing that is like split by the LP is still like close to what you want. That is, hope that the way you model it as LP is accurate enough. That is a strategy. So let's go to it. Okay, so let me define, let's say that G is a weighted graph with like E of G and the weight W of G. And also define like H to be another graph with the same set of vertices, but different H set and different weight. Okay. Now we can define H expansion of a cut to be the ratio of, the cut, like the size of the cut in G over the cut of the side in H. So like you kind of look at the set S, and the thing in the denominator is the same, right? Except that this is now weighted graph. You count the total weight. And the thing below, instead of volume, this is now a more general. It's just something that is defined by some other graph. And you kind of, let's say that there is another graph like which is kind of green. And now you count the edges that cross this. The green edges that cross the same cut. You compare them. Right. And then this is an expansion of a cut. The expansion of a graph is just defined, like denoted by phi of GH. And you just really minimizing overall cut. That is so that this thing is well defined, like it's non-zero. Minimizing overall cut, you get the expansion of a graph. Question about the notion?
So the only connection between G and the H is that they have the same set of vertices.
Yeah. No connection. So for example, like again, suppose that h have one edge, right? From S to T. Then the h expansion would be what? Suppose that h, the green graph, has just one edge from S to T. Then what is the h expansion of a graph? Yeah, it would be minimum weight ST cut, right? Because when is it the case that this thing is non-zero? Only when you cut S and T out of each other, and you try to minimizing over all of those cut. But H can be something else, like it can be a complete graph, for example, or something else. But do you guys remember this notion of D expansion that I defined last time? It's a generalization of conductance, right? That is, instead of defining, so this is like a minimizing over all cuts, the size of the cut over the total demand in S. And recall that if D of U is degree of U, then this is exactly a conductance, right? So I defined last time D expansion of a graph. And now I want to show that this thing, phi of like H expansion, even generalized D expansion. And why is that the case? So let's define, like, given, suppose that you set D, all right? I will define another graph, H, according to D in this way. Let H be such that it's a weighted graph, such that for any, like it's a complete weighted graph, such that the weight between U and V is defined as du times dv over everything, over d of everything. And I will prove that H expansion of the cut for any cut will be like within a constant factor of the expansion of the same cut. Okay. Much better. Okay. So it means that like if you can approximate like H expansion, then you would be able to approximate the expansion within a constant factor. And in particular, you can approximate conductance within a constant factor. And now it's just a matter of algebra. You just need to verify that I will prove that this is the case for every cut. And this is the case because how we define this. So let's just verify this, right? So look at this goal. We want to say that this thing is approximately the same thing as, like H expansion is the same thing as D expansion. And the thing like in numerator is the same anyway. We need to prove that the thing in the denominator are kind of within constant factor. So let's just look at it. This is just the total size of the cut crossing S, crossing the S in the graph H. So you sum up, but H is like complete graph with this weight, right? So for every edge crossing the cut, you have U inside S, V is not in S, and this is a weight. And then let's try to sum over all of this, over all V. You can, for U, you can just put it here, right? So summing over all this, you get this thing, right? And okay, I forget to say that I will just assume that the S is on the smaller side. So D of S is less than half. So that this is true. So that this thing is true, right? Yeah. Now, because S is on the smaller side, V of S is on the bigger side, which is basically almost everything except that is like half. Like within a constant, this is like basically between half and 1. So now this is just a constant factor. Now you're summing up over all this, you get D of S. All right. So now we agree that it's enough to approximate this thing. Okay. Now that's our goal. And okay, let's see. How much time do we have? I think okay. Maybe I should just finish for now. Like I should finish before like 15, right? Is that the 50? Yeah. Yeah, right. So okay. Let me continue actually. Sorry. Yeah. So now so the goal is to approximate H expansion, and so somehow we need to kind of connect it to the cut metric, L1 metric that we talk about. Otherwise, why did we talk about it? So do we have that? So let's just try to look at this, right? This thing is this cut. This is just a cut size, okay, and it's just a sum. You're summing up over all things that cross the cut, okay. Which you can write it in this way too, like summing up over all set of nodes. Actually, summing up over all unordered pair of vertices. And then you look at the weight of this pair. If the weight can be 0 if it's not in the edge is not in the graph. So you just define UV to be 0 if UV is not an edge in the graph. Okay. And and then you just if there is nothing here, then this would just summing up overall weight in the graph, but you would count only the guy that crossed the cut. So this is just like just another way to write down what is the cut size. Summing up all pairs and only and count the weight here, and you count only the one that crossed the cut. Okay. So now comes the the important thing. So let's now which it means that I can rewrite the g of like the h expansion of a graph like this. So know that this is just I try to minimize over all cut s, and for each of given s, I try to I look at the ratio of the cut size in G and the cut size in H, right? And this thing can be written in this way. So which means that this is just a minimization problem over all cut metric. This is just some ratio. Yeah. I mean, nothing really happened. I just rewrite things. And now come a crucial step by Leighton-Rao. You have a problem which is NP hard, and it's a problem about minimizing all cut metrics. The big idea is, okay, what if you try to minimize all metrics, arbitrary metric? Change this thing to any metric. And that is the relaxation. So, by the way, it means, what does it mean? It means that Leighton-Rao relaxation here must be at most this, right? You're minimizing over all bigger set to minimizing over. Yeah. But can it be the case that this thing is much smaller than the H expansion? Because the set that we're minimizing over is it seems like much bigger than before. Instead of just all cut metric, it's any metric. And now the ingredient that you have seen should give you intuition that no, that should be fine, right? Because any metric is kind of close to L1, and any L1 is just a combination of cuts. So because of that ingredient, to next time we will actually show that it's not too small. You have this too. It can be smaller, but not more than log n factor. And that log n factor, where does it come from? From Bourgain. Yeah, exactly. All right, so that's a plan for next time. We will show that, okay, Leighton-Rao relaxation is kind of good indeed. Yeah. So yeah, next time. Yeah. Yeah, see you. Yeah. Yeah. Oh, sorry, I forgot to ask, is there anyone who would like to scribe this lecture? We need someone.
I'll do it.
Thanks. You too. Yeah. Hey.
Hi. So we are now normalizing over. Now we are finding minimum over all metrics.
Yeah.
So, but the metrics can be very small, right? There's no normalizing factor in the metrics, right?
Oh yeah, but you can see that we minimizing the thing that we're minimizing over is a ratio. So
Yeah.
even if you make it
Okay.
small, it's
Okay,
about
yeah,
ratio.
That's true.
Right.
Yeah, because it is ratio. Yeah.
Right. Okay. All right. Hey.
Hey, so I'm thinking of using this problem.
Oh shit. Sorry. Sorry. 1 sec.